Okay, let's start webinar. Today we have presentation by Jordan Okamoto about strongest magnetic fields at the Sun and their statistics. And Dr. Okamoto education is connected with Kyoto University in Japan, where from he got his bachelor's and master and PhD, and he held a number of positions, research position in in Japan, and now he is fellow at National Astronomical Observatory of Japan starting 2016. His research interest concentrated around observational approach to the solar atmosphere and its dynamics, prominences, filaments, and magnetic flux emergence, and using high-resolution field diagrams and spectrometers such as Hinode Solar Optical Telescope and Interface Region Imaging Spectrograph and high-sensitivity magnetographs such as Hinode SOT spectropolarimeter. So please go ahead with your presentation. You have 45 minutes. I will warn you 5 minutes before the end and will
Okay.
interrupt if it's needed. Yeah, go ahead, please.
Okay, thank you for your introduction of me. Okay, today I'd like to introduce my work using a Hinode spectroperimeter, and the title is this one. So let's go. And yeah, as he introduced, this is my self-introductions, and I I don't need to go to the details of this page. So, but if you are interested in that, the bottom right movies is pictures of my inside taken by CT scans when I lived and when uh, I had a surgery of the appendix in the US. And so, okay, yes, here, yes. Okay, so the main topic is about the sunspot, but before going to the details, I'd like to introduce why I started this work. So motivation of this work is I considered what should I do to using to utilize the performance of the high parametric accuracy of Hinode solar optical telescope spectroperimeter. Because I am operation member of a Hinode satellite, and but recently the number of papers using Hinode SP data is decreasing, and I should do something using Hinode data. And Hinode was launched in 2006, and we have a lot of data of Hinode over the last 10 years or now 13 years. And in particular, spectroperimeter or SP here, SP data provides a highest parametric accuracy and also the constant data quality from space. And this is the great advantage for statistical analysis. So I considered what should I do, and I focused on the sunspot. And as you know, sunspot is a concentration of magnetic fields, and typical strength is 3,000 Gauss. But my simple question appears, and that is how large is the strongest one, in particular observed by Hinode. That's my motivation of this work. So what I did first is to investigate magnetic field strengths and their properties of all sunspots observed by Hinode. And in this study, I used the SP level 2 data provided by HAO. Yeah, original SP data is a full stocks spectra of iron absorption line. But this level 2 data provides maps, scanned maps, including field strength, azimuth, inclination, Doppler velocity, or other physical parameters. And it's very easy to use for analysis. So that means I don't need I don't need to do inversion by myself. And I used the data taken over the 10 year, for 10 years from this October 2006 to September 2016. And this data were inverted by a Merlin inversion code developed by HAO or Bruce Wright or colleagues. But the data has a limitation of the field strength up to 5 kilogauss. But many pixels in that data showed 5 kilogauss, and that means those pixels have stronger field more than 5 kilogauss. So I partially used called MIXI inversion code developed by NAOJ Japan, and fitted these pixels again, and I obtained the field strength over the 5 kilogauss. And this 10 years, we have 15,000 scans of SPE, but for Mu-Nethington inversion, the data close to the rim are not good. So I removed some data, and the data number is reduced to 9,000. And I checked the data by my eye, one by one, whether such image includes sunspots or not, and the number is already again reduced. And finally, I sorted these data into active region numbers, and finally, Hinode observed 419 active regions over the last 10 years. And in each active region, I picked up the largest field strength and extracted physical parameters and locations of the strongest fields, such as location, spectral shape. Strongest field is located close to PIA or not, a point inversion line or not, and the region shows the redshift or not, and the horizontal flow exists or not, or something like that. And in this study, about the locations, I categorized the location into 5 types that are umbra or penumbra in large sunspot, or umbra outside umbra in small sunspot. Small sunspot means pores or smaller ones. First, I'd like to describe these types, these small sunspots as pores, but some pores have very faint penumbral structures, and I'm not sure I can say we can call them a pore or sunspot, but that are very small. So I made a new category, small sunspot, relative to a large sunspot, and light bridge. Later, I will show some data about these. And first, I made ranking lists of sunspot field strengths, and this is a summary of the ranking. And the table is very messy, so here let's focus on the first one. First means the strongest fields observed by Hinode. So my first question was, how large is the strongest one observed by Hinode? And the result is 6,250 Gauss. Yes, and so if I'm satisfied with this, my talk is over here, but of course not. So I have to introduce the sunspot with the strongest fields here. And this is the sunspot having the strongest magnetic fields. And the left panel means this one, is a scanned map, a continuum map, which was scanned by spectral parameter. And I show one example of spectra along the white line, and they are shown in the right 4 panels as Stokes I, Q, U, and V. And as you know, I think we can measure the magnetic field strength using splitting videos of the absorption lines. So, for example, here or this one. So this dark part is an umbra, and you can see 3 lines here. But here, much wider spectra appears in brighter regions. So this is a very interesting point of this work. And usually, we use the inversion method to derive the magnetic field strength. But in this case, it's very easy to derive the magnetic field strength without any inversion. Just measure the width. And the result is 6.25 kilogauss in this case. In the light bridge. On the other hand, the strongest field in umbra in this sunspot is up to 4.3 kilogauss. So about 2 kilogauss stronger in the light bridge than in umbra. That's a very interesting point. So here are new question appears. So why does a so strong field exist outside an umbra? That's a very interesting question. Excuse me. And before going to the details of my work, I introduce some previous researches. And one famous paper is by Livingstone, 2006, and they investigated 100-year data, mainly taken by Mount Wilson Observatory, and they measured the Stokes I Zeeman splitting in visible light, and among the 100-year data, the strongest field is 6.1 kilogauss, observed in 1942, I think in World War II. And interestingly, in their studies, only 4 sunspot had the field strength over the 5 kilogauss. And after 1972, there was no sunspot having a 5 kilogauss field. So that means the 5 kilogauss field sunspot is very rare. And another one is by Reza, 2012, and they used the Stokes V profiles observed by VTT tip and in infrared line, and the maximum field strength is 3.6 kilogauss. That's much weaker than the previous one, but this is in infrared, so observed layer are different, and so here the maximum value is not so important. But both researches show a histogram of the field strength, and the left one looks like a Poirot-like distribution, and the right one is a Gaussian distribution. And I will show our result, and our result is different from theirs. And one more interesting is that stronger fields was observed outside the Ambry. So this is not a new discovery, but many authors reported so far. And one example is by Sarah Agrees in 2016, and in her sunspot, the strongest field is located between two umbra or boundary of the umbra. And the region is sandwiched by opposite polarity regions. But nobody mentioned how to generate such a strong field outside the umbra. And I think that's because it's very difficult to track or monitor the evolution of the sunspot for several days from ground observatories because of our seeing weather, nights, and so on. But we have Hinode, and we can investigate the temporal evolution of the strong fields without any obstacles. So I addressed this problem. So in our observations, we had 5-day observations, and we obtained 31 scans. And this is a summary movie of that. The top left one is a continuum map, and the top right one is a absolute field strength. And the lower twos are vertical component and the horizontal component of magnetic field strength. And I draw three color contours by 4, 5, and 6 kilogauss. So green is 4 kilogauss, and yellow is 5 kilogauss. And you can easily find that the stronger field is located on the light bridge. So here, here. And the center of the sunspot, the umbra, also shows 4 kilogauss, but no more than the 5 kilogauss. But in the light bridge, 5 kilogauss field can be seen, and sometimes 6 kilogauss. And this light bridge is sandwiched by opposite polarity, so between this white and black colored umbra. And also this light bridge is occupied by a strong horizontal fields, and the maximum horizontal component is also more than 6 kilogauss. Okay, this is a summary of the movie, but this is movie, and it's hard to track the fine structures. So I prepare, I show 10 snapshots from the movie. So first, again, the strong field is located in the light bridge, but with a closer look at this, in particular, the northern part of the light bridge shows the 5 kilogauss field. And this region gradually decayed for 2 days, from February 1st to February 3rd, and almost disappeared. But during this period, the orientation of the light bridge changes from this shape to this shape, so inclined shape to a vertical shape, and then the stronger field region appeared again in the light bridge, and more than 5 kilogauss, and finally the value exceeded 6 kilogauss, and then decayed again. So this is the evolution of the sunspot. And of course, the interesting point is light bridge. So let's focus on the physical conditions of the light bridge. So I show one snapshot, and the left one is a continuum map, and I draw a umbrella boundary as a white lines in the in the left panel, and also black lines in the other panels. And the middle one is a vector magnetic field map, and the color is vertical component. So yellow is a positive, and green is a negative magnetic field. And horizontal fields are indicated by black bars. The length and the thickness indicate the field strength. So you can see this light bridge is occupied by horizontal, and these horizontal fields are aligned along the light bridge orientation. And the right one, or middle panel of the page, or this one, I mean, this one is a Doppler velocity map, and the blue is a blue shifted, and the red is a red shifted component. And you can see this light bridge is occupied by blue shifted components. And the value is between 1 and 3 kilometers per second. But this sunspot is located, sorry, this sunspot is located, mistake. This sunspot was located, was not located at the disk center, but slightly offset, in particular by 13 degrees from the center, this direction. So if we assume this blue shift component is a projected component of the horizontal flow along the solar surface, the original horizontal flow velocity is can be estimated to be 7 kilometers per second northward or northwestward. And this value is consistent with Evershed flow speed or penumbral flow speed. And this is very important later. And from the velocity map, I found some redshift component at the northern boundary of the umbrella. I mean, here or here. So to investigate these regions, I put the artificial slit here, green line. And this is a kind of streamline along the horizontal fields. And I made a vertical cut along this green line. And that is a right panel, right figure. And P1, P2 correspond to northern end and southern end. And so P2 is in the light bridge, and the P1 is in umbrella. And in the light bridge regions, the most parts show the horizontal magnetic fields, but close to the umbrella boundary, the inclination of the magnetic fields increase. And also our field is stronger than the other regions. And also redshift observed in that region. And I think these features are very important to consider how to make the stronger field. But this is a snapshot, so I checked other data at the different times. The top one is the same as before, and the other ones are taken at the other times. And you can see similar features in all times. So I mean close to the close to the umbra boundary, redshift is observed, and the inclination of the magnetic field increases, and such field is stronger than the other regions. So here and here, or here, for example. So these features are, I think these features are very important. And also maybe this is a little bit different story, but I'd like to identify what is this light bridge, and I call this one light bridge here, but I don't think this is a light bridge because the normal typical light bridge shows a typical light bridge is considered as a invading the granulation from below the sunspot or solar surface. So that means the light bridge shows the weaker fields relative to the surrounding umbra. And in such situations, the filling factor, this is derived by a Milne-Edington inversion. So this is one parameter of that. And the filling factor is very smaller than the other regions in the typical light bridge. But in this case, this light bridge shows a very large filling factors, in particular almost unity. So in that sense, this is not a typical light bridge, but similar to a penumbra, I think, because if we assume this is a horizontal flow, the velocity is 7 kilometers per second, and this is closer to the penumbral features rather than the light bridge. Okay, so from these observational facts, I interpreted what happens in this sunspot, and key feature is these fields are enhanced by a compression of the northern umbra by the penumbral flow from the southern umbra. So this light bridge belongs to southern umbra. Southern umbra means this one. And from south to north, the penumbral flow went towards the northern umbra in this case. And in typical penumbra, or in typical sunspot, the Evershed flow appears from the umbra and go outwards. But in this case, at the end of the float, there is another opposite polarity umbra, and the other umbra also likes to make their own his or her own penumbra, and in this case, the other penumbra is stronger than this northern umbra, and this flow pushes back to the northern umbra, and mass is piling up, and finally the mass is going down to the solar interior. And in this time, the original field strength of the sunspot is just 4 kilogauss, but thanks to the compression, the field is enhanced to the 5 kilogauss with this mechanism. And in the case of this sunspot, the configuration of the sunspot is very complex. So the field is enhanced once, but after that, the configuration of the light bridge or this penumbra in the umbra changed dynamically, and in this sense, the field enhanced once is again intensified by changing configuration of the two opposite polarity ambri, and the 5 kHz field is enhanced to 6 kHz fields. So in that sense, the 6 kHz field is very rare relative to the 5 kHz field, because the original magnetic field strength of the umbra is just a 3 or 4 kHz, and this mechanism happens once the 3 kHz or 4 kHz field becomes a 4 or 5 kHz field, and no more than that. But in this case, this mechanism happens twice or more, and we can get a 6 kHz field. That's my interpretation. And already 30 minutes passed, but okay. And that's my interpretation, but of course, some people think about the flux emergence to generate the stronger fields, because the sunspot and the active regions are always formed by emerging flux coming from the solar interior. And also some apparent features are similar to the scenario of the emerging flux scenario. In our observations, we observed the blue shift between 1 and 3 kilometers per second, and also red shift was observed at the end of the horizontal fields. So that's a very consistent with the scenario of the flux emergence. But I found at least two inconsistencies to explain using this scenario. One is the duration of the blue shift. In our observations, the blue shift persisted for 5 days, and if this is a flux emergence, that's too long for the compact area of the light bridge. The light bridge is just 30,000 kilometers. And the other one is center to limb variation of the Doppler velocity. The observed blue shifted values are larger when the sunspot is far from the disk center, and the sunspot is when the sunspot is close to the disk center, the blue shifted value is very small. So this tendency is completely opposite to the flux emergence scenario, because yes, so that's not consistent. On the other hand, if these are horizontal flows, and this blue shifted component is a projected component of the horizontal flow, the intrinsic velocity is always around 7 kilometers per second at different times. So I think our assumption that these blue shifted components are horizontal flow are more reasonable. And the next one is about the strongest fields. And my title of this talk is the strongest fields, but the stronger field was reported by Van Nolt 2013, and they also used the Hinode data, but the inversion methods are different. They used the spinel inversion method, and also a simultaneous inversion over the 2D regions, considering the point spread functions. So roughly saying, their method is more sophisticated, but I cannot trust their result, because their result is shown in the right panels, and the black one is observed spectra, and the red one is fitted profiles, and the green one is intrinsic Stokes profiles at the single pixel. And they consider the point split functions. So the black one and also red ones are contaminated by the intensity emitted from the surrounding pixels or surrounding regions on the sun. So from the Stokes size spectra, so green line, so we can see a clear 3-Zeeman splitting. So it looks like a very strong field. But in Stokes Q and U, the signal is almost zero, but the intrinsic profiles is very strong. And I think it's too strong, even though they remove the scattered light. But I cannot say more about this. But in their paper, these very strong values, field values, is based on the very broad wings of Stokes V profiles. That means this one here. And this can be only produced by strong magnetic fields near optical depth unity. And this feature appears in this absorption feature in Stokes I. And with this comment, when we look at our own results, our data also show the very strong Stokes V profiles. So unfitted component here, and also this one appears in Stokes I here. So there is a possibility that unfitted, the hidden stronger component exists in also in our results, but that's another work beyond our work using a Milne-Edington inversion. So yeah. And rather than our results, the similar result was published recently and by Azumi Shu Tapir. And she also analyzed the Hinode data, and they found the counter-Evershed flows in sunspots. And so normal penumbra is outward, but in this case, some part show counter-flowing into the umbra regions. And the end point of the flow, the stronger field appears. And in their results, some regions have more than 7 kilogauss by spinor inversion. So this kind of a strong field is not rare in our results or other results like these. So my question was why does the so strong field exist outside the umbra? And my interpretation or my answer is that the penumbra flow compressed the umbra fields to enhance the magnetic fields. But this interpretation is a result from a few cases. So how about other sunspot? So I performed a statistical analysis, but I don't know I have enough time to introduce this one, but let's go to the next. So I analyzed again 419 active regions observed by Hinode, and this is one summary charts. And so where is the strongest field in each sunspot? And the result is half of the active regions show in umbra. And in umbra, in particular, in large sunspots. And 25% in also umbra in small sunspot. So totally 75% of the sunspots show strongest field in umbra regions. And this is a number distribution of the field strength, and well, like this. And this is looks like a log normal distribution, and this is different from the previous works. No, not a simple Gaussian, then not a Paro-like. But I have no interpretation to explain this one, just showing. Okay, let's go back to the ranking list. So the first one is 6.2 kilogauss. But as I showed, the 75% of the sunspots show strongest field in umbra regions. But in top 30, half of them are in light breach, not in umbra. And also, penumbra also are ranked here. And just 8 active regions
have 5 more minutes.
Okay, thank you. Just 8 active regions have the strongest field in umbra regions in top 30, and the other 22 are at light breach or penumbra. That's very interesting. And okay, let's skip the examples, first, second, and third. So to consider how to make the strongest field, it's important to focus on the other parameters, so close to PIL, redshift, or horizontal flows. And these show the 25%. The answer is yes. So, and this, you can imagine, this 25% is similar to the other 25% at the top chart. And your guess is correct. And these 25% active regions has a stronger field than the others in all cases. And actually, the 89 active regions have all of these 3 features simultaneously, and they have a stronger field. And such and the sunspot having such features are located mainly in non-umbra regions. So the non-umbra, the sunspot with the strongest field at the non-umbra region, the number is 105, and the other one is 300 or 14. But at the top of 3 lines, rows, most of them show the 3 features simultaneously. And in this case, 84%, that is 88 over 105 of the strongest fields outside the umbra have these 3 features simultaneously. And that is consistent with our hypothesis that is a horizontal flow compressed the magnetic field at the other umbral boundary. So these statistics support our hypothesis. Okay. And this is one example to show the mechanism clearly. So the pictures are very messy, but the top left one is a continuum map, and the center of this map shows the strongest field regions. And the left bottom 5 panels are enlarged view of the white box. So the center of the field of view is the location of the umbral boundary, the strongest field, and this is located at the umbral boundary. And this sunspot is located. This white circle is a solar disk, and this dot is the location of this sunspot. So the normal penumbra from this umbra is northward or eastward. And these are observed as a blue shifted component in Dopplograms. But only here shows red shift. And if we assume this is horizontal flows, this is a backward penumbral flow. And at the end point of this flow, the field shows the strongest, and which is consistent with our hypothesis. Okay, so already 45 minutes passed, so let's go to the summary. And if you have a questions, I will go back some skipped pages. Okay, so the conclusion is the 75% of active regions show the strongest field in Ambri, and the other 25% outside the Ambri. And the other 25% active regions get high in ranking of the field strength, and 84% of them have these physical features. And this is consistent with our hypothesis. And this result statistically supports the mechanism that the strongest fields are generated by kinematics on the photosphere. And also, this is not directly attributed to the internal origins. So this is a summary page. So this is final page, and the top two lines are already explained. And one comment is this strong field is generated by motions on the solar photosphere. So that means this strong field is not reflecting the solar interior. So if you are interested in the solar dynamo or 11-year solar cycle, you should focus on only Ambri, not the strongest field on the solar surface. Okay, so very quick, but that's it about my talk. So thank you very, very much.
Okay, thank you very much for your talk and a nice presentation. Now we have plenty of time for questions or comments, so please go ahead. If you have any, you can unmute your microphone and ask a question. While all microphones are muted, I meant to ask about that other paper reported more than 7,000 Gauss magnetic field. So I think I was puzzled with these few reports of strong magnetic field in September 2017 in your paper and in that one. And what I have done, I checked if there is any Cornell counterpart in the form of georesonant emission at really high frequencies. And what I found for the case of September 2017 or for the case of your 6,000 Gauss, I saw this Cornell contribution, high frequency georesonance source. But in case of that 7,000 Gauss, I did not find any hint of the corresponding Cornell counterpart. So this raises some doubts from my side that in that case, such strong values were really present in the data. So that's just general comment.
Yeah, this 7 kHz field is located very deep in the very deep layers. So and also are very compact regions. So it's not so important in the coronal regions, I think. Yeah, actually.
Yeah, at least there is no independent confirmation of a strong magnetic field at that case. That would be my more conservative comment.
Mhm.
Again, other questions or comments? Dale?
This is Dale. I have a question about the Livingston results, which that distribution went all the way down to about 1,000 Gauss, but I noticed your distribution does not. So is this just a matter of spatial resolution, do you think? The Livingston?
Yes. You mean the weaker regions or stronger regions?
I'm talking about the 1,000 Gauss measurements in
here.
Livingston. Yeah.
Yeah, in Livingston, yes. They did not show any rollover at low values.
Right. Actually, I don't know how to measure the magnetic fields by Livingston. Yeah, because they use very old data, and I don't think a calculation was well done. And also resolution effect also exists. Yes, right. I checked I performed one test about the dependence of the spatial resolution, and for example, the left one is our data, and the maximum value is 5 kilogauss. But I generated raw resolved data, and in that case, of course, the measured value is very weak relative to the original one. So in Livingston case, some region includes non-magnetic regions, and the field becomes weaker. But I don't think this is the main result. But where is it? But calibration is not good in the old data. So I think that's the reason. And recently, I forget who, but Yanil Chak or somebody has a report about the sunspot and the umbra. Umbra should have a magnetic field more than the 1.8 kilogauss, and less than that, the umbra disappears, or just plage-like features, also G1 bright point region features or something like that. So I am skeptical to this 100 and between the 100 and 200 sunspot here. This should be dropped down here.
Okay. The other point that I think the Livingston paper was making was a general decrease in the maximum field strengths over time. But it looks like with appropriate resolution, you get perfectly high field strength. So, so do you think that was maybe a premature result?
So yes, the method of observing method becomes improved in time, and they observe the correct value in the recent data using a recent data. But in old case, the instrument itself is not so good, and the value may be not good. Yeah, but I don't know how to derive these values by them. So yeah, I need to ask him.
Okay, do we have other questions? I do see all microphones muted, so in this case, let me thank the speaker again, and yes, I will place materials online soon, and next one will be in 4 weeks from now. Thank you. Goodbye.
Thank you for listening. Thank you.